going to do is we're going to actually look for, okay, this velocity of the green vector right here when we're looking from the shore. Because the boat is heading in this direction, but the current's going to drift the boat back downstream. So even though the boat's heading in this direction, it's actually going to follow this green arrow rather than this purple arrow. Because the purple arrow is heading, blue is the drift, so it's going to be going like this. All right? So let's do the part A first before we even go to part B. So what is the velocity of the boat respect to shore? That's V boat respect to shore, BS. And that's just the green V. All right. So from our equation, V is equal to V prime plus U, or velocity of the boat respect to shore is equal to velocity of the boat respect to water plus the velocity of the water respect to shore. So I'm keeping the water or current or wind speed. It's going to be blue. And this is the boat's velocity respect to water in the bathtub. Okay. So this is the boat's velocity with no current. And this is with current and the boat together, added together. So when I draw this thing out, it was like this, and this is the VBS. So when I broke this up, the purple vector, which is the VBW, I redrew it here, and I broke this up into its x and y component. So the x component is VBWX, which is VBW times cosine of this angle theta, 60 degrees. So when we do that, we get 5 times cosine of 60, which is 2.5 meters per second in the x direction. And in the y direction, VBWY is VBW times sine of theta. And theta, again, is 60 degrees, so 5 times sine of 60, you get 4.33 meters per second y hat. So if we combine these two to give the velocity of the boat with respect to water in Cartesian form, we have 2.5 x hat plus 4.33 y hat meters per second. So this vector is that, right here. Now, let's take a look at velocity of the current, the water with respect to shore. The blue is going straight horizontal in the negative x direction, right, relative to our xy coordinate system, right? So here, if we were to look at this velocity, it's only going to have the x component but zero y component. And since it's going in the negative x direction, we have negative 3 meters per second x hat as our u, or VWS. So if we were to put this in a Cartesian form, look what we have. We have negative 3x hat plus 0 y hat meters per second. This vector here is this. So now we can add these two vectors, which are these two vectors, in Cartesian form, and then get the resultant of my VBS. All right, so let's do that. So here we go. So I'm going to rewrite down this VBW, which is equal to, right, 2.5 x hat plus 4.33 y hat, right? Of course, this is in meters per second. And then VWS, which is the velocity of water with respect to shore, is negative 3x hat plus 0 y hat meters per second. So when I add these two vectors up, I get my resultant vector of VBS, boat respect to shore. All right? So when I add the x components together, I get negative 0.5 x hat plus, here when I add these two y components together, I get 4.33 y hat meters per second. Okay? Therefore, when I actually find, if I were to look for, um, if I were to look for the magnitude of this, right? If I were to look for magnitude of this, the magnitude of this is simply the Pythagorean theorem of these two components, which is 0.5 squared plus 4.33 squared. And when you do that, I think you'll get something like 4.36 meters per second as the speed along this direction right here, which is right here this way. Okay?
Thank you all for your cooperation this morning as we review the lockdown protocols. Have a great day, Conestoga.
We're still alive. Yeah. So this is the magnitude of my boat respect to shore. Now to find the angle. So since if I were to redraw this green vector, right, separately, so here's my V boat respect to shore, BS. This will have its components of, I guess, y, VB as y, and the VB as x, right? So this is the angle right here that we could figure out, this angle right here, okay? So this is VBSY, and this is VBSX. Here's my VBXY, and here's my VBSX. So theta is equal to tan inverse of, right, tan inverse of, here, VBSY over VBSX. Therefore, my theta is equal to tan inverse of, right? VBSY is 4.33. VBSX is, you could put negative 0.5, but it just means that it's going to be, going clockwise. When you get an angle, it's negative, right? So since it's a reference angle, you could just put 0.5 in there, right? So if you work that out in your calculator, I think you'll get something like 83.4 degrees, which makes perfect sense because this is very close to like almost 90 degrees here. Right? So this 83.4 degrees is from the shore of downstream, right? Okay, so 83.4 degrees, right, is from the shore of downstream, okay? Oops. Downstream. So this is my A, okay? That's my A. Now let's take a look at B. For part B, how far, no, if the river is 86.7 meters wide, so if the river itself is delta y, here is the width right here this way, right? And that is 86.7 meters wide. How long will it take to cross this thing, right? Well, if you were to think about it, when you're crossing this, it is this VBSY is what's really you're concerned about, because you're only going this distance in the y direction with only this velocity. Does that make sense? Right? Because we're only looking at the y direction, so we should only look at the y velocity. So we should look at the VBSY, because that's the velocity that's going to be going in the y component. So we already know delta y is equal to VYT plus 1/2 a sub yt squared. Well, this boat is not accelerating, so we know this acceleration in the y direction for the boat is 0. We know my delta y, which is 86.7. We know Vy, which is VBSY, which happens to be 4.33 times time t. So when we solve for time, my time comes out to 20 seconds. So it takes 20 seconds to cross the stream, across the river, in this case. And now for part C, so this is part B. For part C, how far, right, downstream will the boat be from a point directly across where it started? So if I were to look at this diagram again, if I were to go straight across, this is where it should, be for the other side directly from where I started. But because of this going this way, it's going to end up downstream about this much. Does that make sense? Okay. So how much downstream will it land at the other side? So here is the river again. Right? Because of the drift caused by the current, we will have to work with VBSX. And that happens to be 0.5 meters per second in the negative direction, right? So you could put the negative there if you want to. Right? Therefore, the time that it drifts down is going to be exactly 20 seconds, just like how much time it takes to cross, right? Therefore, I want to know how much delta x is from where it should be to where it is downstream. Okay. So my delta x is equal to, right, VBSXT plus 1/2 AT squared. Well, there is no acceleration for the boat in the x direction. So again, this whole term drops out. So my delta x is equal to VBSX is negative 0.5 times time, which is 20 seconds. So my delta x happens to be negative 10 meters, or 10 meters downstream from directly across the starting point, right? So 10 meters downstream or downriver, right? From point directly opposite starting point. Okay? Voila. Any questions?
Mr. Ken, I have a quick question.
Yes, Aiden?
Where did you get that formula for C?
This right here?
Yeah.
This is equation number 3. I mean number 2.
Oh, right, okay.
Remember? And so is this.
Yeah.
This is also equation number 2. I just wrote it as delta x, but if you think about it, you could write it as x final is equal to x initial plus v I x t plus 1/2 a sub x t squared. Remember that?
Yeah.
Yeah, and y final is equal to y initial plus v I y t plus 1/2 a sub y t squared. So these are basically, if I bring this, the initial position to the other side of the equal sign, it becomes change, right, negative, so it becomes y final minus y initial, becomes change in y. Same thing with this. If I bring the x initial to the other side of the equal sign, it becomes negative x initial. So x final minus x initial becomes delta x. All right, any other questions? All right, we can move on. All right. All right, so here we go. All right, let's take a look at the next problem. Again, I will post these solutions in PDF format so everybody has it, so you can look at it. So, okay, here we go. A motorboat whose speed in still water is 3.6 meters per second. So, which V is this? This is the V prime, all right? Or otherwise known as VBW, boat respect to water. Okay? And it is aiming upstream at 27 degrees, right? With respect to the line perpendicular to the shore. So this is the 27 degrees right here. So what is this angle right here? What is this angle? Hopefully you know that. It's complementary angle of that 27.5, which is 62.5 degrees. Hope everybody can get that. All right. So this is 27.5 degrees. Now, if this boat aims in this direction, because of the current from the river will make it drift downstream, the boat will actually travel straight across. Got that? Okay? So even though the boat is aiming this way, right, because of the current bringing you back down, the boat actually travels straight across the river. Okay? So even though this looks really complicated, it's not. Because here, let's think about this. Let's draw this thing out, what the VBW is. Obviously, this will have VBWX and VBWY components, right? So here, we know it's going to have VBWX, and we know it's going to have VBWY. This angle here is 62.5 degrees, like we said. So let's find the VBWX and VBWY, okay? Because we already know what VBW is. This is 3.6 meters per second. So we can say VBWX is equal to VBW times cosine of 62.5 degrees, which is 3.6 times cosine of 62.5 degrees. So my VBWX, the x component of my purple vector, is 1.66 meters per second, x hat. Okay? And then what about y hat? Well, let's see. VBWY is equal to VBW sine of 62.5 degrees, or simply 3.6 times sine of 62.5 degrees. So my VBWY is equal to, I get something like 3.19 meters per second y hat. Okay, so we can say my VBW is equal to 1.66 x hat plus 3.19 y hat meters per second. So that's good to know. Now, let's take a look at the water. VWS, or simply the U, right? This is V prime, by the way. This is U. We don't know what this is. We don't know the value. So I can simply just say my VWS is equal to, I know this is x direction only. Therefore, I can say VWSX, x hat, because it can't be, this is not zero, obviously. It has to be some value, but we don't know what this value is. But we do know in the y direction it is 0 y hat. Does that make sense? Right? Because we don't have anything in the y direction, it's only in the x direction, but we don't know what this x component value is, but we just write it as a variable, we don't know. So here's the second vector, VWS. Now we know V has to be, both respect to shore, has to be, right? These two added together, right? It has to be VBWX plus VWSX x hat plus, right, plus VBWY plus VWSY y hat meters per second. Does that make sense? However, since my VBS is going straight up across, so this is my VBS, what's my x component for my VBS? 0. So this, we know it has to be 0. So VBS is equal to 0 x hat plus VBSY y hat meters per second. So we know that this has to be 0, right? So we could set this up. So here we can say VBWX plus VWSX must equal to 0. But we know that this is 1.66 plus VWSX is equal to 0. So we can calculate what this is. VWSX is equal to negative 1.66 meters per second x hat. So now we know what that is. That is in negative 1.66 meters per second. We also know that VBWX plus VWS, I'm sorry, this should be Y, this should be Y, I already finished X, is equal to VBSY. We know that this VBWY is 3.19. We already know that WSY is 0. So we now know what the VBSY is. So our VBSY is equal to 3.19 meters per second y hat. So what is the speed of the current? There it is. The speed of the current is that. All right, so for part A, we know VWS is equal to, right, negative 1.66 x hat plus 0 y hat, right, meters per second. So the speed of the water current is equal to just 1.66 meters per second. This squared plus 0 squared square rooted is just going to be this. So that was easy. And for part B, what is the resultant speed of the boat with respect to shore? There it is, right? So for part B, right, the resultant speed, VBS, is equal to, basically, 0 x hat plus 3.19 y hat meters per second. So the resultant speed, VBS, is just the magnitude of this, which is 0 squared plus 3.19 squared, and then you square root that, and you'll get 3.19 meters per second. Booyah. We know the direction. Direction is straight up, right? So perpendicular to the shore. All right. Any questions?
Mr. Kim,
Yes?
I have a quick question.
Question.
So how do you know that VBWX plus VWSX equals 0?
Because it's going straight across, right? So this does not have any
Sorry, I
x.
can't see the figure.
I'm sorry. This does not have any x component,
Wait, that is true.
right? And because it doesn't have any x component, that I know this x component has to be 0,
Yep, that makes sense.
right?
Got it, thank you.
Yep. Any other questions? All right. We'll move on. All right. Modern day warrior means stride. Today's time saver. All right. Anyway, Huck Finn walks at speed of 1 meters per second across his raft this way in the y direction, positive y direction. That is, he walks perpendicular to the raft's motion relative to the shore. So he's walking perpendicularly this way in the y direction. And the current is going this way to the positive x direction at 2.7 meters per second. Okay? Relative to the riverbank. So this here is U, or simply VWS, right? This here is V prime, or simply V, I guess you could think of it as, I don't know, Huck respect to raft. See how it gets crazy? Like all these different, you know what I mean? So that's why I like to use U and V prime. Just makes more sense. Because like, okay, what the heck is HR, Human resources? You know what I mean? So it just really kind of defeats the purpose of all these subscripts. So I rather use V prime and U in this case, which will be less confusing. And because this is happening from the observer, from the shore, we will see Huck moving like that. Is that right? So let's draw this out. Okay, let's draw this out. So here, I'm going to try to scale it out so Huck Finn walks 1 meter per second this way, which I'm going to call that V prime. Right? And then the U happens to be 2.7. Right? So that's going like this, right? That's U. So my V, which is Huck respect to shore, this is my V. I hope that makes sense. Okay. So what is my V prime? Right? Because we always use V is equal to, right? V prime plus U. This is our bread and butter right here, right? So let's find out what V is, and let's find out what U is in Cartesian form. So my V prime is equal to, this looks like 1 meter per second, only in which way? Only in? Good, all right, yeah. Does that make sense to everybody? So 0 x hat plus 1.0 y hat only. Right? And for U is 2.7 meters per second. but only in the x direction, right? So here, for my u is 2.7 x hat plus 0 y hat meters per second. Therefore, if I add these two vectors up, I just basically add the x's and add the y's separately. Oops. My u, or my v, I'm sorry, my v is equal to v prime x plus ux, which is 2.7 x hat, plus 1.0 plus 0 is just 1.0 y hat meters per second. So to find the magnitude of my v, the magnitude of my v is nothing more than the Pythagorean theorem. And that should come out to 2.88 meters per second. Okay. And then for angle theta. Now theta, you could measure this angle here, or you could calculate this angle here, or you could calculate this angle here. It doesn't really matter. But I'm gonna actually just calculate, because here is my 2.7 and here's my 1.0, right? Looking at this. So here's my angle theta. I'm going to calculate this theta relative to the shore upstream. All right. So theta is equal to tan inverse of, right, opposite, which is Vy over adjacent, which is Vx. Right. So my theta is equal to tan inverse of, right, 1.0 over 2.7, and that comes out to 20.3 degrees. From, right, from the shore upriver, right? From the shore upriver. Therefore, my V is equal to, right, 2.88 meters per second, comma, theta is equal to 20.3 degrees, right, from the shore upriver. I hope that explains it. All right. Now let's take a look at page 14. Page 14. Now let's take a look at this very carefully. This, we have, boat is actually aiming straight across the river, but the current's going to make it drift downriver, so it's going to actually travel diagonally across the river. Okay? So this is actually easier then, really, right? So here we go. A boat can travel 2.3 meters per second in still water. So which V is this? Which V is that? V, V prime, or U? Still water. V prime is correct. That's my V prime, which is this. boat points its prow directly across the stream whose current is 1.2 meters per second. So what's 1.2 meters per second? That is my U. Correct. So this is my U. So this is my V. Okay? So if I were to draw this thing out, right, it will be, here's my V prime. Let's see if I can draw this thing out. So here, here's my V prime, and here's my U. Okay, here's my U. And here's my V. Here's my V. And they want us to find this theta here, right here. Okay. All right. So what is the velocity, magnitude, and direction, right, of the boat relative to the shore? It's just relative to the shore. But why did it give us this theta? So this is relative to the shore. I think maybe we have to find this theta right here. Okay. So this is really not the. This is the reference angle. Okay. So here we go. Here we go. We know we always start with this V is equal to, right, V prime plus U. All right. So let's find the V prime and U in this component forms. That's pretty easy because these are all on X and Y axis, right? So my V prime is really nothing more than 0 x hat plus 2.3 y hat meters per second. The U is equal to negative 1.2 x hat plus 0 y hat meters per second. So what is my V? So when I add these up, my V is equal to, I get negative 1.2 x hat plus 2.30 y hat meters per second as my V. That means if I were to redraw this, okay, if I were to redraw this, of course I'm doing this a little bit bigger. So here's my V, and here's my Vx, and here's my Vy. And since they want us to find the angle respect to the shore, this is the theta that we're looking for, right? So theta is equal to tan inverse of, right, tan inverse of Vy over Vx. So theta is equal to tan inverse of, right, Vy, which is 2.30 over Vx, which is, again, even though it's negative 1.2, I'm just going to put positive 1.2 because it is a reference angle. Right? So my theta is equal to, I guess, 22.4. Just let me see. So tan inverse of, right? 2.3 divided by 1.2, right? So 62.4. Well, 62.4, right? So 62.45 And of course, if you were to find the V's magnitude, that is square root of 1.2 squared plus 2.3 squared. And if you do that, I think you'll get something like 2.59 meters per second as your magnitude of that, right? So what does that mean? That means my V is equal to 2.59 meters per second, comma, theta is equal to 62.45 degrees, right, from the shore downstream, okay? Downstream. Yeah, I see. They gave us this angle right here, but I think it says since relative to the shore, so I
Oh, that was right, okay.
yeah. So I think like this is kind of misleading, you know, because it says relative to the shore. I found the relative to the shore rather than relative to the perpendicular to the shore. Alrighty. So that was part A. Right, that was part A. So part A, right? All right. What about part B? What will be the position of the boat relative to the point of origin after 3 seconds? Wow. Wow. So how far away would the boat be from the origin after 3 seconds? Well, after 3 seconds, it's going to travel along this direction for 3 seconds. That means it will travel in the y direction as well as in the negative x direction for 3 seconds. Does that make sense? So let's find the position for when time is equal to 3 seconds. Let's find what the x final position is, right? According to this to be my 0, comma 0, right? So this is my 0, comma 0. So my x final is equal to x initial plus vix times time plus 1/2 a sub x t squared. But there's no acceleration for my boat, so this is 0. So my x final, when t is equal to 3 seconds, is equal to, my x initial, I'm going to call that 0 because that's where my starting point is, plus vix is basically negative 1.2 meters per second. So negative 1.2 times time, which is 3 seconds. So my x final comes out to negative 3.6 meters x hat. And then for my y final is equal to y initial plus viyt plus 1/2 a sub yt squared. Again, there's no acceleration in the y direction for my boat, so this whole term drops out. So my y final is equal to 0 plus 2.3 times 3.0 seconds, and I get 6.9 meters in the y direction. So the position of my boat at 3 seconds is equal to negative 3.6 x hat plus 6.9 y hat meters. That's where I'll be. That's where I'll be. Okay? So that's my part B. Then, last one, I'm going to make you guys do this for points. Page 15, 5, and 6. Do this, save it as PDF, and upload it onto Schoology, all right? So that's going to be your homework grade. So let's take a look at number 4 before I let you do that. Here, I have two planes approaching each other, right? I have two planes approaching each other. So here we have my F-117 stealth fighter, right? Going at 835 kilometers per hour, right? So this thing is going at 835 kilometers per hour. So here's my velocity going 835 kilometers per hour. And then I have another plane, right? We have MiG. Right? We have a MiG flying at 835 kilometers per hour. They're playing chicken to see who's going to bail out, right? The distance of separation between the two planes happens to be 10 kilometers. How many seconds do they have in order to avoid the head-on collision? So most likely they're gonna go like that, like the well, I guess if you want to go right, bear right this way, and the other one's gonna go that way. All right. So they're playing chicken. How do we solve this? You know, relative to this guy, this plane's coming at how fast? This speed or this speed relative to this person? Let's say you're driving down the highway going 50 miles per hour and you see another guy coming at you at 50 miles per hour. How fast is that guy coming at you? 100. Yeah, 100. Right? Because relative to you, you're not moving, right? Relative to yourself. So that guy's coming at you at 100 miles per hour, you know? So according to this guy, this red plane is coming at like 1670, 1670. So remember from the video, right? V is equal to V prime plus U, right? But this U here is, right? I think he did it as minus whatever, right? He did minus. So V, let's do it the way he did it. So VA, and then this is VB. Okay. So VB respect to A is equal to VA minus VB. So velocity of B respect to A is equal to 835 minus, this is obviously in the opposite direction, is a negative 835 kilometers per hour, right? Negative. So velocity of B respect to A is